In this lesson, we're going to look at why certain materials conduct electricity. And I'm going to tell you a basic principle. And from that principle, you're going to be able to make predictions for many, many different substances. And whenever I teach this lesson, I always think about this quote from Einstein, that imagination is more important than knowledge. So after this lesson, you're going to come away with a very, very small piece of knowledge, but that piece of knowledge will be powerful enough to apply to almost any substance and make a really important prediction about electrical conductivity. So why do objects conduct electricity? An electric current is a flow of charged particles. In order for something to conduct electricity, it must have two things. Number one, there must be charged particles. And number two, they must be free to move. Now, in a familiar context, you've come across electricity in physics, where the charged particles are electrons, and they are free to move through wires. You know that electrons are delocalized in metals. So that makes sense with what you know already. But let's take a look at some other examples. Now, throughout this lesson, I want you to bear these two things in mind. We need charged particles that can move. Let's look at this table. So on the left-hand side, we have a whole range of different substances. We've got liquids and solids, and at the bottom we've got AQ, which means aqueous, which stands for dissolved in water. And for each of these substances, we're going to ask ourselves, does it contain charged particles? Can the charged particles move? And then based on those two things, is this substance going to be an electrical conductor? So let's start with liquid water. Does it contain charged particles? Okay, the answer is no. So covalent molecules have no charge. Okay, so water does not contain charged particles. Can the charged particles move? Well, we had no charged particles in the first place, so the answer is no. So we've got a no in both columns. So is water an electrical conductor? No. Let's have a look at graphite. So graphite, from the bonding topic, does it contain charged particles? Yes, we know that graphite contains delocalized electrons. And that word delocalized implies that those electrons are free to move. So we have a yes in both columns. And whenever you have a yes in both columns, then you have an electrical conductor. And that makes sense because we know that graphite is an electrical conductor. Let's have a look at sodium now. So sodium is a metal. And you know that metals contain delocalized electrons. Electrons are charged particles, and the word delocalized means free to move. So we have a yes in both columns, and as expected, sodium, metal, is an electrical conductor. Okay, I don't think there's anything groundbreaking so far. Let's have a look at something a little more complicated. Sodium chloride. Well, sodium chloride is ionic. It contains positive sodium ions and negative chloride ions. So yes, we do have charged particles. We have charged ions. Now, you've known since the start of GCSE that in a solid, the particles are in fixed positions, and although they can vibrate, they cannot move from those positions. So sodium chloride contains charged particles, but they are not free to move. So we have a yes in the first column and a no in the second column. And overall, that means that no, we do not have an electrical conductor. And again, That makes sense. Sodium chloride is table salt. You would put it on your food at a mealtime. And I think it's intuitively obvious from everyday life that salt is not an electrical conductor. Okay, so what happens if we take that sodium chloride and we heat it to about 800 degrees Celsius and we melt it? Well, we still have charged particles, ions, but you know, since the beginning of GCSE, that in a liquid, the particles are free to move. So actually, liquid sodium chloride contains charged particles that are free to move. And so using our prediction, yes, sodium chloride should conduct electricity. And in fact, if you do an experiment, you will find that sodium chloride in the liquid state does conduct electricity. Let's think about sodium chloride AQ, which remember means sodium chloride dissolved in water. Does it contain ions? Well, yes, once again, it contains sodium ions and chloride ions. Are those ions free to move? The answer is yes. The ions are dissolved in water, and when something's dissolved in water, it's just like a liquid, particles free to move. We have a yes in both columns, and that means that sodium chloride dissolved in water is an electrical conductor. Let's take a look at a common experiment. So we've got lead 2 bromide, PbBr2, and that is an ionic substance. That makes sense because lead is a metal and bromine is a non-metal. So we would expect metal, non-metal to form an ionic substance. And we also expect it to have a high melting point. So it's going to be a solid at room temperature. So just as a reminder, as a solid, this ionic substance cannot conduct because the ions are not free to move. The particles in a solid are not free to move. They're in fixed positions. But as a liquid, if we melted it, it can conduct because the ions now in the liquid form are free to move. And so we can actually show this using quite a well-known demonstration. So we've got a setup here. We've got a crucible at the bottom containing lead 2 bromide. And dipped into that, we have 2 electrodes. So an electrode is just a piece of inert electrically conducting material. Normally, it's graphite. You could use platinum, but normally you would use graphite, which is obviously just made of carbon. We've got a battery at the top, and we have a lamp. And initially, when we have this experiment, we would have solid lead 2 bromide, which it does not conduct. Okay, and if you look at the circuit, if we have solid lead 2 bromide, we do not have a complete circuit and the lamp will not light. But when we heat the lead 2 bromide and we allow it to melt, it will suddenly become an electrical conductor. And when it becomes an electrical conductor, it completes the circuit. And the lamp should light up. And this experiment proves that lead 2 bromide is an electrical insulator when solid, but an electrical conductor when liquid. And a common exam question would ask something like, why is solid lead 2 bromide an electrical insulator? The answer is because the ions are not free to move. Equally, they might ask, why is molten lead 2 bromide an electrical conductor? The answer is because the ions are free to move. Now there's a video on YouTube that I have put into the comments section below this video that I recommend that you watch. And that video just shows you this exact demonstration shown on this page.